Hi guys, welcome back to Data Every Day. Today we're looking at a data set of skin lesion images. The image data is actually given as a series of pixel values in a data frame, or a CSV file. And we're going to try to predict the type of lesion. Some of them are cancerous, some are not. But at the end of this column list we have a label column with values between 0 and 6. So there's 7 different possible values. You'll notice that the distribution of the classes is very skewed, so I'm not sure what kind of results we'll get, but we're going to try to predict the type of lesion based on the rest of the data. So let's go into the notebook, and we're going to use a TensorFlow convolutional neural network to make our predictions. So I'm importing NumPy and pandas to work with the data, then matplotlib.pyplot and seaborn for visualization. I'm then using the train test split function from sklearn to perform a split on the data, and we'll create our model with TensorFlow. And then afterwards we'll analyze the results with a confusion matrix and classification report from sklearn. So I'm going to go ahead and import all that, and I'm going to load in the data using pandas.readcsv. And I can grab the file path right over here. I'm going to be using the 28 by 28 underscore L CSV file, which is essentially 28 by 28 grayscale images, and they are encoded as vectors of pixel values. So there are 784 pixel value columns. Note that the square root of 784 is 28, so this is actually 28 by 28 images, just flattened out into a single vector. So let us start pre-processing. Let's take a look at if we have any missing values. I doubt we will, since it's image data, and we do not. We just want to check. And I guess the first thing I'm going to do is split off the label from the rest of the data. So I'm going to call the labels y. That's going to be data sublabel, and I'll make a copy as well. And x is going to be data.drop label from axis 1, and I'll make a copy of that as well. Alright, now I'll just paste this in. I got this from the dataset provider. There are 7 possible labels. They are different medical conditions. Some of them are cancerous, some of them are not. And if we take a look at the value counts, y.value counts, you'll notice that we have a huge percentage of them are concentrated into this particular condition. And in some of them we have so few examples, it's hardly even accounted for in the data. So I'm not going to deal with the imbalanced data today, but if you wanted to improve this balance, you could do some data augmentation, where you take images from the underrepresented classes and perform transformations on them to sort of create more artificial data based on the data that we already have. For example, you could do rotations, zooms, stuff like that, to try to sort of create some more data in the underrepresented classes. Alright, but like I said, I'm not going to do that today. I'm going to create a label mapping, which is going to be a dictionary that's going to map each label value, each integer, to the name that is given. And I'll just copy that in as well, just taking each one of these little indicators that were provided along with the number that is actually in the data set, and going to create a mapping that we can reference later. Alright, so first thing, if we're going to start pre-processing properly, I guess I shouldn't call this pre-processing. Yeah, why not? No, we'll say, whatever. I'll keep it as pre-processing. And now we're going to rescale the data, although this is technically pre-processing as well. So what I want to do is rescale the pixel values between 0 and 1. This will improve the performance of the model. So it'll ensure that all of the the values of each column will be constricted to a range of 0 and 1. To do this is very simple. Currently x is this thing. If we just divide x by 255, that will apply an element-wise division onto each cell in the data frame, and that will do what we're looking for. The reason I choose 255 is because these are pixel intensity values between 0 and 255. So if we divide by the maximum value, we're essentially scaling the data down to be between 0 and 1. So I'm going to make that the new x, and we can take a look at it after. And then I'm going to reshape it. So let me just paste this in what I have. Currently, each image is represented by a vector of length 784. We want images of size 28 by 28, so let's reshape each vector into a 2D array of the proper size. For this, we can just use numpy.reshape or x.reshape. However, we actually want to make the images into 3D arrays with a dummy dimension for the single color channel. That's because TensorFlow's convolutional layers require a color channel as well. So we're gonna let's see. All right, first let me just turn x into a NumPy array. So currently it's in a data frame format, but I want to turn it into a NumPy array just so that I can get the I can use the reshape command. And I just want it as a NumPy array in general. It's nicer. I'm gonna print out the shape as well. So currently we have 784 long vectors and 10,000 of them. So what I'm going to do now is x.reshape, and I'm going to specify the new size in here. -1 will indicate keep this dimension the same, infer the dimension. So -1 here corresponds to the 10,000 examples. We don't want to mess with the 10,000, so we're keeping a -1. And then 28 by 28. Now if we look at that, we can't really visualize it, but look at the shape of it. You can see we've now reshaped the 784 into 28 by 28. And I want to see, can we put an extra dimension? We absolutely can. We just add that one extra dimension for the color channel. So that's going to be our new x. Make sure that we don't have shape on there. And then we can print the new shape of x. Alright. So let's visualize a few of the images. Visualizing. Alright, so let's take a look at a few of the images. What I'm going to do is I'm going to sample the data really quickly. I'm going to get like 9 random images that I want to display along with the labels. So to do that, we can use Panda's sample function. But currently the data is now in NumPy array form, so I'm just going to temporarily switch it back to a Pandas data frame. Actually, I'll use a series, because we don't really care about preserving the columns. So I'm going to create sample data, which will just be a copy of the data, but it will zip together x and y, because we want to make sure we sample the x and the y at the same time. And zip will just pair up all the x data and all the y data into tuples for each example. And we want to turn that into a list afterwards. And then we are going to turn it into a series, and then we're going to sample 9 images. Then we're going to split it back into x and y when we're done. So sample x and sample y. Sample x is going to be sample data dot apply. Basically what this is saying is just grab the first element of the tuple, which will be the x, and y will be the second element, which will be the y. You see, we're just sort of like extracting them back out from the sample data. And this, we actually have to turn it back into a NumPy array now. This is a bit annoying, but this is what we're going to do, because we did convert it into a series. So, okay, this is good to go. This got a little messed up. If we look at, here, I'll show you now. If we run this and I look at sample x, it looks right, but actually, if we look at the shape, we have to restack it. So there's 9 images, but each 28 by 28 image is currently it's like they're NumPy arrays inside NumPy arrays rather than it being just one big NumPy array. So note that if we call the numpy.stack function on it, then it will, oh wait, sorry, the period should be out. Then it will properly bring back the data as we had it. So numpy dot, whoops, right here, numpy.stack. Okay, now sample X should have the proper shape, which is 28 by 28 by 1 images and 9 of them. And sample Y should just be 9 labels. And sample Y just looks like this. That's all the different label values for each image that we sampled. Okay, now that we have some sample data, let us plot them. So I'm going to create a new matplotlib figure with a figure size of 12 by 12. And then for I in range 9, so for each image, we're going to create a new pyplot subplot in a 3 by 3 grid, indexed by I plus 1. That's just because subplot requires that the first index starts at 1. And then plt.image this will show an image given pixel values. And we're going to pass in sample x sub I. Now, I just want to note that the image show function, it doesn't like this extra dummy channel here, this dimension. So we're going to take off that dimension with the numpy.squeeze function. That will just squeeze off any extra dimension like that. So this will show the image, and then we want to get the label for the image. I'll call it image label. This is going to be, well, we have our sample Y sub I, which is the actual label. However, this is as a number, right? And let's get the mapping. I just want the name instead of the number, because it doesn't mean much to show the number there. So all we have to do then is take the mapping and pass in the number to the mapping to get the name. Then we will title each subplot with the image label. And we will turn off the axis tick marks. Alright, and then let's show. And so this is 9 different images. Not the most pleasant to look at, but you can see that each one is labeled with the corresponding condition from the mapping that we have. Alright, so let's do a train test split. This is very simple. We're just going to split the set into train and test values. So we're going to use the train test split function from sklearn. We're going to split x and y the same way with the train size of 70%, and I'll include a random state as well. This will just this function actually shuffles the data too, so that we don't have to do it ourselves. And the random state will ensure that the shuffle and the split is always made the same way, so that we can reproduce the results. And now this will generate 4 new sets of the data: x train, x test, y train, and y test. And there we go. Okay, we can begin modeling. So, like I said, we will use a 2-dimensional convolutional neural network to extract features from the images while we train. So the idea behind a convolutional neural network is that the model can learn to identify different aspects of the image by essentially looking at little windows of the image and like learning patterns it sees through convolutional layers. I'm not going to go too in depth about that, but if you want to take a look at it, go research it. It's very cool. I'm going to set up an input layer with tf.keras.input. The shape will be 28 by 28 by 1. And let's give it a name as well. Just be the input. Alright, then we'll have the first convolutional layer, tf.keras.layers.conv2d. We've give it a number of filters. This is essentially how big is our window. 16, and then a kernel size. Kernel is basically, I'm not going to go too in depth about it, but a kernel size of 3 is pretty standard, so we'll keep that. I will make a video about convolutional neural networks and explain in depth the processes, but for this I'm just going to sort of give a quick overview. So we're going to just name that conv1, pass in the inputs here, and then we're going to max pool after that. So essentially, this will create a lot of values. We want to sort of bring it down to a simpler version after that. That's a very basic way of describing what's going on here. tf.keras.layers max pooling 2D, and we'll give it a name as well, max pool 1. I'm going to pass in the output from conv1. Then I'm going to copy this over 2 more times. This will be the second one. The only difference between them is that we're going to increase the filters each time. Here we'll have 32, here we'll have 64, and this is a pretty standard architecture for a convolutional neural network. I'm just going to go ahead and get all these 1s and turn them into 2s, because that is what we're dealing with now. I think that should be all of them. And then over here we'll have 3s, right? Okay. Then we'll flatten it. Actually, we'll do an average pooling. So, average pooling essentially takes a bunch of it takes a two-dimensional set of data. At least the well, let me get the. It's tf.keras.layers.global average pooling 2D. This will take a two-dimensional array of values and sort of average their values down into one vector. So let's give it a name, average pool, and we're going to pass in the values from max pool 3. Okay, and now we'll get our outputs. This will be tf.keras.layers.dense, and remember we had 7 classes, so these will be the 7 probability values that an image that we generate for each image, where the highest one will be our classification. So the activation here is going to be a softmax activation, which will ensure that all of these 7 values are probability estimates, and we'll give it a name, output. Here I'm going to pass in the average pool output so that it feeds through all the way, and then we'll create our model using tf.keras.model. The inputs here is just going to be the inputs layer, and the outputs are going to be the outputs layer. Alright, then we'll print the summary of the model, and we'll plot the model with tf.keras.utils.plotModel. Passing in the model here. Here's the summary. You can see we start off with a 28 by 28 by 1 image. Then as the notice we have the graph has disconnected. It's not going it's actually going straight to 3, and that's because inputs was passed in here. This should have been max pool 1, this should have been max pool 3, and I actually have this misnamed this. It should be conv3. Okay. Oh no, I did something wrong. So inputs is coming in here, conv1 goes to here, max pool 1 goes to here, conv2 goes to here, max pool 2 goes to here, conv3, max pool 3, average pool. Okay. Alright, so this is what it really looks like. Okay, so you see we have a 28 by 28 by 1 image that gets sent to a 26 by 26 by 16 vector, and then the max pooling brings it down to 13 by 13 by 16. The next convolutional brings it to 11 by 11 by 32. These are just the filter sizes that we specified over here, 16, 32, 64. And then conv3 brings it to a 3 by 3 by 64. Max pool 3 brings it to a 1 by 1 by 64. And then the average pooling is unnecessary actually here because we only have one value. But that brings it down to a 64. And I noticed that we're getting very small dimensions here. I might actually remove one of these. And I'll add it back in later if we get better results, but I didn't realize this before. Okay, so we're just going to use 2 convolutional layers now. So it ends up coming down to a 5 by 5 by 32. That gets averaged down into a just one vector of length 32, and that gets sent to our final predictions. And you can see this is the route it takes. It comes in through the input, then our first convolutional and max pooling layer, then our second convolutional and max pooling layers, and then finally gets average pooled and sent to our output. Okay, and now we will train the model with an atom optimizer and sparse categorical cross entropy loss function. Cross entropy loss is also called log loss. It's a way of measuring how far off a prediction is from its classification. So sparse categorical just means we're doing it for a multi-class setting. And we're going to compile the model with an atom optimizer, which is generally considered the most powerful optimizer, and a sparse categorical cross entropy loss function. And the metrics, we're just going to use accuracy because it's multi-class. Keras just doesn't support too many multi-class metrics. Batch size here 32, epochs 50. So I'm going to train for 50 epochs, and I'm going to employ early stopping, which will stop the training once our model stops improving. So the history, we're going to store the model's fit history in history, and we're going to fit on xtrain and ytrain. Then our validation split will be 20%. Batch size will be, that's the batch size we specified earlier, and number of epochs will be the epochs we specified as well. Then I'm going to include this callback function, tf.keras.callbacks.early stopping, and with this callback we monitor a value, in this case the validation loss, and when the validation loss stops improving after a set number of epochs, let's say 3, then we'll stop the training and we'll restore the weights from the best epoch. So we're going to say restore best weights equals true. And now we'll train, and let's get the results while it trains. So first thing is I want to just get the accuracy on the test set. So model ac equals model.evaluate x test y test. So it's going to generate predictions and compare them against the actual labels. And I'm going to turn off verbose mode. And then we'll print out test accuracy. We'll display it to 3 decimal places and give it a percentage value. And format that string with model ac. This actually should be just the first value. This evaluate function will return the loss and the accuracy for the test set. We just want the accuracy, so we're doing sub 1. And then I want to multiply it by 100 to get it in a percentage form. Alright, so we got a 66.75% accuracy, and it's not too bad, but we have to remember the classes are really skewed here. So 66% accuracy is not necessarily good, because if we consider this is probably about 66% of the data alone. So let's say we guess 4 every time, we're still getting 66% accuracy. I think if we divide this by the length of y, we'll actually get the percentage. Oh wow, it's actually almost exactly 66. So our model may not be doing well at all, but not bad. I just want to see if we add in the third convolutional layer and max pool layer. I want to see if that actually improves or inhibits our performance. So I'm just passing these in properly, and I'm passing in max pool 3 here and giving a 64 on the filters. Okay, so now we just have 3 layers, 3 sets of convolutional layers. So I'm going to retrain, and then I'm going to generate some predictions. So y true, these are going to be the true label values. This will be given by y test, which we already have, but I just want to turn it into a numpy array. And then ypred is going to be the predictions that we generate using model.predict on xtest. You can see it already stopped, and it's about the same, maybe a little higher. nothing crazy, especially considering the class distribution. But yeah, let's get this. So we get our predictions, and this actually is going to return the raw probability values. You can see it actually returns 7 probability values per example, where each one is the probability value for a given class. So if we want to just get the label associated with this result, we're going to look for the highest probability value. And the way I can do that, let me just show you down here. If we use numpy.max on a given, let's take a given example. This is just one example. And yes, I know that it's not showing all of them here. So this is sort of, this is only showing 1, 2, 3, 4, 5, 6 of them. But I just wanted to show you because if we use numpy.max on there, it will return the highest value. So one of these got a 62%. If we use numpy.argmax, we can get the index of the highest value. So this is saying the third index 3. And so this is actually the class, right? Because we encoded our classes from 0 to 6, if we index it, we'll get the actual class value. So what I want to do is I just want to map this argmax function to each element in model.predict. So we can do that with the built-in Python function map. We can map a lambda function that takes x and returns numpy.argmax of x to model.predict. And so that will look, we'll have to display it as a list when it's done, but that will actually return label classifications for each value. So that's what I'm going to do here. I'm going to apply this essentially. Grab this, paste it here, except instead of model.predict, I'll just do ypred since we already generated it. And I'm going to apply this function to it. And then after, I just want to store it as a numpy array rather than a list. So now if we look at yTrue, we should have an array of true labels. If we look at ypred, we have an array of predicted labels. Alright, so now let's get a confusion matrix. This is from sklearn. We've got to pass in yTrue and pass in ypred, call it cm, and I'll also get a classification report also from sklearn, passing in yTrue and ypred, and I want to set the target names in the classification report to target names will be label mapping dot values, so that's the actual names of the classes rather than just the numbers. Okay, and we'll call that one CLR. Okay, and this is not a good warning that we're getting. This is saying that precision and f-score are ill-defined and being set to 0 in labels with no predicted samples. So this happens when one of our labels got no predictions. And because we have values in every single label, for one of them to get no predictions means our model is probably not doing such a great job. But let's take a closer look. Let's look at the confusion matrix and the classification report to really get a sense of that. So I'm going to create a new matplotlib figure here with a fig size of 8 by 8. That will give us a nice grid for the confusion matrix. And we'll use the Seaborn heat map to generate the confusion matrix in a nice graphical way, passing in CM here, turning on annotations. I'm also going to format it just so that this will allow us to get integer value counts for our predictions rather than seeing them in scientific notation. And then the minimum value I want to set to 0. That's just going to set the minimum color value to 0 rather than the minimum of what we have. Then C bar is the color bar I'm turning off. We don't need to see that. And I'll give it a color map. I'll use the blues color map. Okay, and then I want to plot the x ticks. So the actual tick values. I don't want to see 0, 1, 2 all the way to 6. I want to see the actual. Well, actually, let me show it so I can explain what this is doing. This is what our confusion matrix looks like. It's already looking really bad. You can see one of our classes is getting way more predictions than all the others. So this is probably due to the imbalanced data. Additionally, class 3 and class 5 have no predictions at all. So I'm going to label these so that it makes more sense. We will first give it a title, confusion matrix, and I'm also going to give labels on the axes. So the X label will be predicted, the Y label will be actual. So these are our predicted values. These are our predicted classifications, and these are the actual classifications. Now, if you look at the diagonal here, the diagonal is showing the correct classifications in each category. So for class 0, we had 7 correct classifications. For class 1, we had 19. For class 2, we had 48. For class 3, we had 0. For class 4, we had 1918. Our class 5, we had 0 here. And class 6, we had 52. So last thing I want to do here is I want to display these labels as the actual text labels rather than just as numbers. So what I'll do here is plt.xticks. That will set the ticks. First, we have to specify the spacing. I'm going to use a numpy.arange with 7 values to get spacings. And if I use that, it will actually set it to just the very edge here. So I want to do plus 0.5 to center in the middle, like this one. And then the values we're going to use are actually going to be taken from label mapping .values. And I can use the exact same thing for the Y ticks. So this will just be Y ticks. Okay, and now you can see the actual text labels here along the edges. Maybe I'll make this a little bigger. We'll do 10 by 10. Alright, so yeah, now let's look at it. It's not good. All of the predictions were made on this AKIEC target value, and you can see that's actually the one that's label 4 that has all the examples in it. So 6 and 2 are to look out for next. They're the next highest value counts. And 6 is this one. And we got, it was alright. Out of all of our predictions, we got 52 of them right, and 36 in the wrong category here, 24 in the wrong category here, and a few other mistakes. I guess we got a majority of them right here. That will be reflected by the precision score of that column, which if we print the classification report, we can see it. So DF, the precision score, is 42. That means out of all of our predictions, we got 42% of them correct, which is not good. This is saying a lot here. Look, we have 0 for precision and recall in BCC and in VASC. So that's because we have no predictions in those categories. And you can see we have in those categories actual values for them. This y-axis represents the actual values, and there were 45 plus 3 plus 1, so 49 total values for VASC, and 45 of those 49 we predicted incorrectly as AKIEC. So that will be given by the recall score for VASC. You can see for the recall we have 0 because out of all of the actual VASC values we predicted 0 of them correctly, so 0%. I guess the only one we can really look at here, I mean 2 was also the one with the next highest values. That would be BKL. In BKL we have not good either, 32 and 15 precision and recall. The F1 score is sort of a combination of the two, so this will give us a sort of overall sense of how each label is doing, and you can see that the only one with any substantial results is the AKIEC column. So that had an 82% F score because we have a really good recall on it. That just means that out of all the actual AKIEC values, we got a large portion of them correct, actually 96% of them correct. So you can see that there's very few misclassifications on this column, on this label, but for all the others we have terrible results. So it's not really saying much. And then not only did we do well recall-wise, but our precision isn't even that good. Like, this is saying that out of all the ones we predicted as AKIEC, which is this column here, we got 72% of them right. But we're still misclassifying a lot of the other ones as AKIEC as well, even though it is, we do obviously have some ability to predict it correctly. So my suggestion here to improve this model, I'm not going to go into it, but we could use data augmentation to, like I said, to fill in more examples for the underrepresented classes, hopefully to get all of them up to this level. We could also do is just sample a few of these so that we're not using all of them. Problem with that is that we lose a lot of data, but you know, there's a trade-off. If we it's called upsampling, where you generate more samples from the underrepresented classes to try to match the most represented class. That way you're using sort of fabricated data. And on the other hand, if we downsample, which is we remove some of these to balance it out, we're losing data. So it's a trade-off there, but that's the best way, one of the best ways to deal with imbalanced data. Another way we could do is using class weights in the training, although that that will weight different classes differently in the loss function. But I don't have a lot of success using that. It usually just inhibits the performance. I'm not sure though. It might be useful here. I'm going to stop it now. If you want to hop into my notebook and try out some of these things I'm suggesting, go ahead. And you can let me know how it goes in the comments below. But that will conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.